Computer Science 63. Computer Science 63. Computer Science 68. 68. Computer Science 68. Electronics 41. Electronics 41. ETB 41. Mechanical Engineering 49. MEB 49. MEB 49. MEB 56. Sorry, MEB 56 present. Sorry, actually he has joined late. Sorry, sorry. MEB 6060. MEB 60. MEB 060. Metallurgy 3030. Metallurgy 3030. Mining 26. Mining 26. Mining 26. Mining 3030. Mining 3030. I have called only the absent roll numbers. That means the other students are present.
Ma'am,
Ma'am, EAB049.
ITB057.
Okay. Now I will share the screen and then start.
Ma'am, I'm
Ma'am,
ITB
Tell me.
B057.
I
I joined late.
ITB one by one, please. ITB 57.
Yes, ma'am.
ITB
B57.
57 I have given.
Okay, ma'am.
ITB 57 I have already given. You have joined late, but I have given. Any more?
Yes.
Ma'am, EAB049.
EB049. Okay. Electrical Engineering 49. Electrical 49 I have already given.
Ma'am, Electronics
Actually, I
31.
have checked twice and after that I have given. Then
Thank you. Ma'am, Electronics 35.
Electronics 35.
Ma'am, CET 91.
Why are you repeating? Why are you repeating? I have given your attendance. I did not call your roll number.
Okay, ma'am. Sorry, ma'am.
You are CB 91. I have called your roll number.
Yes, ma'am. Yes, ma'am.
CB 91.
I joined late, ma'am. Actually joined late, so.
Okay, okay. You have joined late. Okay. CB 91. Yes. You have joined late. Now I am giving you attendance. Okay.
Thank you, ma'am.
Now I have given. Okay. May I start now? I think I should start now. Okay. Okay. Can you see the screen? All of you?
Yes, ma'am. Visible.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Okay, now I start. Okay. And I have sent the course material part 3 to all of you. I think all of you have received. Okay. Now now I start. You see, particular integral for the function. You see, capital X, which is a function on the right side of the ordinary differential equation. And you have already observed in the previous course material that if capital X equals to exponential function like e to the power x, then there is some rule for finding particular integral. Actually, the rules for finding particular integral will depend on the function capital X. Capital X means a function which lies on the right side of the ordinary differential equation. For different forms of capital X, these rules will be different. Already you have observed when capital X equals to exponential function like e to the power ax. And today I will discuss the case number 2, where capital X, that means a function on the right side, equals to x to the power m type, where m is actually non-negative integer. Actually, m is non-negative integer. M is non-negative integer. Okay. So the rule is this. You see, 1 by fd x to the power m. This is the particular integral 1 by fd operating on capital X. Now here capital X is x to the power m. Then what you have to do? You have to take this 1 by fd means fd inverse. That means fd inverse operating on x to the power m. Actually, fd inverse will be expanded in ascending powers of d like this. Just fd inverse in the numerator. 1 by fd means fd inverse. If you write this in the numerator, and then fd inverse will be expanded in ascending powers of d like this. You see, like this. Where actually you see this S0 plus E1D up to AMD to the power m. This is actually expansion of FD inverse in a series of ascending powers of D, and most important thing, and suppressing all the terms beyond D to the power m, since dr, that means rth order derivative of x to the power m equals to 0 when r is greater than m. Just I am explaining all these things. If you see this example, then after that I will explain this thing that will be helpful to you. Actually, what does it mean? It means actually rth order derivative of x to the power m equals to 0 where r is greater than m. You just take some examples. Say second order derivative of x. Suppose m equals to 1, r equals to 2. Here we consider that situation where order of the derivative is greater than the degree of the variable. Suppose r is 2, m is 1. So second order derivative of x, that is 0. Suppose it is r equals to 3 and m equals to 2. So third order derivative of x square is 0, or third order derivative of x is 0. So you see, if r is greater than m, then rth order derivative of x to the power m will be 0, provided r is greater than m. Or that means order of the derivative is greater than the degree of the variable. That is observed in this problem. You see, you see this problem. This is fd. You see, this is fd operating on y equals to x to the power m, where m is 3. Okay. Now you see, same as before, you first solve the equation whose right side is 0. And choose y equals t to the power mx as the trial solution of that differential equation whose right side is 0. And you have already found that solution, how to obtain. You see, first write down the auxiliary equation, and that auxiliary equation is this, where just we replace d by m. This is the shortcut formula for finding the auxiliary equation, and then we find out the roots of the auxiliary equation, and we observe here the roots are 0, 0, 1, 1. So we obtain 0, which is repeated twice, another root 1, which is also repeated twice. So 0, 0, 1, 1, 0 root is repeated twice, 1 root is also repeated twice. So we use the formula for finding the, you see, this solution whose right, you see, we solve the differential equation whose right side is 0, and that solution is actually called complementary function. And you see this 0 is repeated twice, 1 is repeated twice. So the formula should be like this: c1 plus c2x e to the power m1x, where m1 root is repeated twice. Another equal root is m2, which is 1. First root 0, m1 is 0 repeated twice. Another root m2 equals to 1, which is also repeated twice. So the formula is this to write down the complementary function. C3 plus C4x e to the power m2. M2 means here another root, which is 1. Just to use the previous formula already computed, already you have observed, already you have used in the previous class. So this part is known to all of you. Now today I will discuss to find a particular integral where the right side function is of this type x to the power m. That means here x cube. We have to find out the particular integral where the right side function is x cube. You see 1 by fd. Fd means here, you see, if you break this into factors, then this should be d squared d minus 1 whole square, like this, d squared d minus 1 whole square. And you know, you have to take this fd in the numerator, so you should write d minus 1 whole square. We may replace d minus 1 whole square by 1 minus d whole square, because 1 minus d whole square should be written in the numerator with negative index. And you know, for negative index, the binomial should be 1 plus x or 1 minus x type. To expand this binomial, you see, for negative index 1 minus d whole to the power minus 2, just to expand this, that should be 1 plus 2d plus 3d square plus 4d cube, etc. plus dot 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 operating on x cube. What is done here? Just you see, this function fd is written in the numerator with negative index, and then we expand this 1 minus d whole to the power minus 2 in ascending parts of d, that I have told you a few minutes ago. Just you see this, which, what is it? Just you see, this is the expansion of fd inverse in ascending parts of d. Actually this series is infinite, but you see, if you write this plus dot dot dot, you may write this plus dot dot dot, but you see 1 into x cube, d operating on x cube, that is first order derivative of x cube, then d square operating on x cube, then d cube operating on x cube. Okay, but after that d to the power 4 operating on x cube will be 0, because you know, I have already told you derivative, rth order derivative of x to the power n equals to 0 whenever r is greater than n. So if you write here a m plus 1 dm plus 1, etc., etc., then if you operate m plus 1th order derivative on x to the power m, or m plus 2th order derivative of x to the power m, then the values of those derivatives will be 0. So this plus dot 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 terms will actually contribute nothing. That will give you 0 values. So you see here in this example, you see, just you see d cube x cube, which is actually factorial 3. Okay, then you see d4, fourth order derivative of x cube, fifth order derivative of x cube, that should give 0 values. So the non-vanishing terms or non-zero values are this: 1 into x cube plus 2 into first order derivative of x cube plus 3 into second order derivative of x cube plus 4 into third order derivative of x cube. Third order derivative means here actually factorial 3, that is actually 6, and 6 into 4, that is 24. Just simplify this. Now you see 1 by d square. Already I have discussed in the previous class that 1 by d stands for integration with respect to x. So it is actually 1 by d that operation will be repeated twice. That means 1 by d, 1 by d. First apply 1 by d, that is just you integrate once with respect to x. That will give x to the power 4 divided by 4, 6 into x cubed by 3 plus 18 into x squared by 2 plus 24 into x, like this. After that, again 1 by d, if you apply, that means again integrate with respect to x, then it should be x to the power 5 by 5, x to the power 4 by 4, x cubed by 3, x squared by 2, and after that it will be simplified and obtain this value. What is done here, just you observe, just you see this FD, when it is taken in the numerator with negative index, you have to expand in ascending powers of d, and then you have to apply this on this function x to the power m, which lies on the right side of the ordinary differential equation. And this is an example where it is done. We first solve the equation's right side is 0, find out the roots of the auxiliary equation, then we write down the complementary function. After that, we find out the particular integral, where you see this FD is taken in the numerator with negative index and then expand in ascending powers of d. And after that, you see we apply these operators on x cube, which is a function on the right side. And after, in the meantime, you have already observed that rth order derivative of x cube equals to 0 provided r is greater than 3. And so all these terms containing d to the power 4, d to the power 5, etc., etc. That is higher order derivative higher than 3. If we apply on x cube, then the value of the derivatives will be 0. So this is the last term, non-vanishing term, d cube x cube. That is third order derivative of x cube, which is actually factorial 3. And then factorial 3 means 6, 6 into 4, that is 24. This is the last non-vanishing term in this expansion. Finally, we get this result, and you see the complete solution is given by complementary function plus particular integral. Just we have added both complementary function and particular integral and obtained the required complete solution. Next, number 3, particular integrals for capital X, which is sine function or cosine function. That means the function on the right side is sine x or cos x. A is the coefficient of x in the sine function or cosine function. Now you see 1 by FD operating on sine x. You see this may be sine or cosine. The process remains the same. This rule remains unchanged. If it is sine x, sine ax or cos ax, what we have to do? You see, first you express FD as a function of d square. If FD contains only even powers of d and we denote it by phi d square, suppose it is function of d square of this 1 by FD. If FD contains only even powers of d, then it is denoted by function of d square. Sine x remains unchanged. And after that, you replace d square by minus a square. What is a? A is the coefficient of x in the sine function or cosine function. Note this point very seriously, that d square is replaced by minus a square, not minus a whole square. Note this very seriously. D square is replaced by minus a square. That means as a whole, you see this is negative number. Because a square is always positive, so minus a square is always negative, provided this denominator phi minus a square is not equal to 0. So if you write down instead of sine ax here cos ax, then the process remains unchanged, the formula remains unchanged, and the result becomes this denominator is phi minus a square, like this. Just you have observed this in the previous case, and then it is cos x, provided the denominator is not equal to 0. Now we apply this rule to solve this problem. You see, here you see this is function of d. Okay, right side is cosine function. Here you coefficient of x is 1. in this case sine ax or cos ax. Here this coefficient of x is important because you see the square is replaced by minus a square. What is a? Is the coefficient of x in the sine function or cosine function. Now you see, again we first solve the differential equation whose right side is 0, like this. You see, you first see the equation whose write down the differential equation whose right side is 0. Then we write down the auxiliary equation. Then we solve this auxiliary equation and find the roots as 4/3 minus 2. That means the roots are real and distinct. If the roots are real and distinct, then you know the formula to write down the complementary function. So it is C1 e to the power m1x plus C2 e to the power m2x, where m1 is 4/3, m2 is minus 2. This is actually complementary function. But we are interested here to find out the particular integral. That is 1 by fd. Fd means this. Actually, if it is resolved into linear factors, then it should be 3d minus 4 into d plus 2. Like this, you see. 3d minus 4, d plus 2. 5 cos x. Now, interesting thing is this. The denominator should be expressed as a function of d squared. You see, the formula is this. This fd should be expressed as a function of d squared. So, we apply this. You see, it is 3d minus 4. So, it should be multiplied by 3d plus 4 to make it a function of d squared. Similarly, d plus 2 should be multiplied by d minus 2 to make the denominator as a function of d square. And finally, you see d square should be replaced by minus a square. What is a? A is the coefficient of x in the sine function or cosine function. So you see here you see cos x. That means a is 1. A is 1. Coefficient of x in the cosine function is only 1. So this d square will be replaced by minus 1 square. You see, because 1 is the coefficient of x in the cosine function. Again, this d square is replaced by minus 1 square, like this, minus 1 square, like this. Now just simplify this denominator, which is 25. And the denominator, you see, numerator is this. Just you see, we have multiplied both numerator and denominator by 3d plus 4 and d minus 2 to make the denominator as a function of d square, and then d square should be replaced by minus 1 square, where 1 is the coefficient of x in the cosine function. And after simplification, the denominator becomes 25, but numerator becomes this. Now it is very simple to calculate second order derivative. 3d square cos x means 3 second order derivative of cos x minus 2 first order derivative of cos x, that means d cos x minus 8 cos x. Then you obtain this result. Then complementary function can be obtained by adding complementary function and particular integral. So complete solution is given by y equals to complementary function cf plus particular integral pi. We have computed both complementary function and particular integral. Add them to find the complete solution. Am I audible?
Yes, ma'am.
Yes, ma'am.
Okay,
Yes,
and
Yes,
also
ma'am.
it is visible. The screen is also visible, right?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes,
Okay,
ma'am.
okay. 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 Okay.
Thank you, ma'am.
Now you see, okay. Now you see another case number 4. You just recap. Firstly, we have considered in the previous class where the right side function capital X is exponential function like e to the power x. Next, today we have discussed this situation where the right side function is right side function capital X is x to the power m, where m is actually non-negative integer. Okay, and after that we consider case number 3 where particular integral for capital X, where the right side function capital X is sine or cosine function. Now we are to discuss another case, case number 4, where we are to find out the particular integral where capital X equals to e to the power x into v. We have considered only e to the power x case, case number 1, but now it is e to the power x into v, where v is a function of x or a constant. Capital V is a function of x or constant. Okay. Now you see, if it is there some problem? Some sound is there. I do not know from where it is. There was some sound. Just a minute. Verify. Yes, Vicky. Okay. Okay. You see,
Ma'am, who will take our class test?
now the right. Okay, what are you telling? I can't listen. Sorry.
Who will take our class test? Class test.
Class test.
Yes,
Class
ma'am.
test.
Yes, ma'am.
No, I will not take your class test.
Okay, thank you, ma'am.
Okay, I will not
Okay,
take your
ma'am.
class test.
We will ask
So,
another teacher.
so you will. Are you telling something more?
No, ma'am. No, ma'am.
No, ma'am.
No, ma'am.
You continue, ma'am.
Okay, I can proceed.
Yes,
Yes,
ma'am.
ma'am.
Yes.
Yes, ma'am.
Okay, you see another situation where we face this capital X equals to exponential function e to the power x into v, where v is a function of x or a constant. You see, the rule is this: just e to the power x is taken outside the operator, and here d is replaced by d plus a. D plus a. A means the coefficient of x in the exponential function. D is replaced by d plus a. V remains unchanged. This is the rule. Just you see, e to the power x and v will be separated by this operator. You see, e to the power x is taken outside the operator. D is replaced by d plus a, and v remains unchanged. This is the rule. How to apply this rule? See this problem. Suppose consider this problem. Third order differential equation. And you see, firstly, we have to solve the differential equation whose right side is 0. And already you have observed capital D stands for ddx, and so we just replace ddx by capital D operator and obtain d cube y, capital D 3y, third order derivative of y, minus 5d squared y plus 8 dy minus 4y equals to the right side, where right side actually exponential functions, but you observe these things very seriously. You see why. Firstly, we solve the differential equation whose right side is 0, same as before, by considering e to the power mx as the trial solution of the differential equation whose right side is 0. And then we write down the auxiliary equation, and you know how to write down the auxiliary equation. And you know how to write down the auxiliary equation just by replacing this d by m. We can write down the auxiliary equation very quickly. Then you solve this auxiliary equation and find the roots as 1, 2, 2. Now you see the root 1 is different, okay, but 2 is repeated twice. So this is the combination of these two formulae. You see 1 e to the power m1x plus c2 plus c3x e to the power m3x. Okay, this is the complementary function. This is actually the solution of the differential equation whose right side is 0. So we have written this complementary function. After that, we have to find out the particular integral like this. 1 by fd. Here fd is actually this. D minus 1, d minus 2 whole square. You see this. If we factorize this, then it should be d minus 1, d minus 2 whole square like this. You see, this is fd. The right side capital X is this. Now you see this step is very important step. Okay, you see 1 by d minus 1 d minus 2 whole square e to the power 2x. Just you observe, this is exponential function, and you know the first rule. What is it? Just you have to replace d by this coefficient of x, that is 2. If you replace d by 2, then you get d by 2 plus 8 dy minus 4. then this factor, okay, no problem, but this, what happens to this? And you are allowed to replace this d by this coefficient. That means if you are to replace d by 2, provided the denominator is non-zero. That is important. So in the first case, d minus 2 will create some problem. In the second case, you see d minus 1 creates some problem. Only in the third case, you see d is replaced by minus 1, so there is no problem in the third term only. So what you have to do, if you replace d by 2, no problem. So we replace d by 2, no problem. So replace d by 2, but this cannot be 1 by d minus 2 whole square e to the power 2x. You see, this in this case, d cannot be replaced by 2 because denominator becomes 0. So you can replace d by 2 in the first case. In the first term, provided denominator not equal to 0. That is applied here. In the second case, d is replaced by 1 because 1 is the coefficient of x in the exponential function. So second factor creates some problem. In the second factor, no problem, but first factor creates some problem. So in the second term, just replace d. In the second factor d by 1, but this d minus 1 remains unchanged. In the third case, you have applied this formula. In the third case, you can replace each of this d by minus 1 because these two factors are non-zero. So what we have obtained? So this is constant, okay? Now 1 by d minus 2 whole square e to the power 2x. Now you see where you have observed that if you replace d by 2, the denominator becomes 0. Then you consider this as e to the power x into v type. That means you applied this formula. What you have just observed, e to the power x into v type. This formula will be applicable when the denominator becomes 0. If the function is exponential function, but if we replace in the denominator d by this coefficient of x in the exponential function, the denominator becomes 0. In that case, you apply this formula. Where e to the power x into 1, as if e to the power 2x may be written as e to the power 2x into x to the power 0 type. So in this first and second term, you see e to the power 2x into v, this formula, e to the power x into x to the power 0, e to the power x into v, where v is a constant here. Similarly, in the second term, you see 1 by d minus 1 e to the power x, where if d is replaced by 1, the denominator becomes 0. So we consider this as e to the power x into 1. 1 is actually x to the power 0 type. So in this first and second terms, you observe that e to the power x into v type. Now the formula is this e to the power 2x will be taken outside the operator, and d will be replaced by d plus 2. D will be replaced by d plus 2, but v remains unchanged, so 1 remains unchanged. Similarly, in the second term, you see e to the power x will be taken outside the operator, and d will be replaced by d plus 1, but v, that is 1, remains unchanged. You see, we have applied this formula. This formula here, and now we just simplify plus 1 minus 1 will be cancelled. Now it is 1 by d operating on 1. 1 by d operating on 1. 1 by d operating on 1 means actually it is integral of 1 with respect to x. Similarly, in the first term, you see the plus 2 minus 2 will be cancelled, and then 1 by d square. 1 by d square operating on 1. You see 1 by d square means 1 by d will be applied twice. That means you have to integrate twice. Firstly, you integrate 1 with respect to x, that is x only. Secondly, you have to integrate again to obtain x square by 2. So 1 by d square, that is you integrate twice, then you will get this 1 by d square operating on 1. That means integrate 1 first time, that will give you x, and again integrate x with respect to x, that will give x squared by 2. But here in the second term, 1 by d operating on 1, so it just integrate 1 first time, that will give you x, and again integrate x with respect to x, that will give x squared by 2. But here in the second term, 1 by d operating on 1, so it just integrate 1 with respect to x, that will give x only. And this is the simplified value of the particular integral. So here we have applied this formula e to the power x into v. This formula, v is actually considered here a constant. You see here v is a function of x or constant. So we may consider v as 1, like this. So I think this is the complete solution with this. This is the complete solution the complete solution, where you see first you have written the complementary function, after that you have written the particular integral. Okay, so you see in this case where the formula is this: when the function on the right side is e to the power x into v type, first you take this e to the power x function outside the operator, and d is replaced by d plus a, d is replaced by d plus a, but v remains unchanged. So we have applied this formula here, e to the power x 2x into 1, because you see, if you replace this d by 2, then denominator becomes 0. So number 1, formula number 1 or case number 1 cannot be applied here. Case number 1, that is where the capital X function on the right side is e to the power x, can be applied only when the denominator is non-zero. But here you see, if we replace d by 2, the denominator becomes 0. So you are not allowed to apply case 1 or formula 1. Similarly, in the second term, if you replace d by 2, the denominator becomes 0. So you cannot apply first formula for finding the particular integral, where the denominator becomes 0. So in these cases where we consider this exponential function, but denominator becomes 0, in that case you may apply this formula. Just consider v as 1. V we consider as 1, that is a constant, and then you apply this formula. Today I stop here. Okay, up to this.
Okay, ma'am.
Ma'am?
Yes,
Ma'am?
yes,
Ma'am,
yes,
actually, this time I came 15 minutes late in the start of the class. Could you please mark me present? I thought of asking you in the end.
Okay, 15 minutes late, but AMB 25.
Yes, ma'am. AMB is 025.
Okay, now I have given. Any more?
Thank you, ma'am.
Yes, ma'am.
Okay.
Me, Shubhankar Mondal. Ma'am, me.
Shubhankar Mondal.
Yes, ma'am.
Why? I am calling only the absent roll number. Be serious. Be serious. I am calling only the absent roll numbers. Civil engineering 78. Civil engineering 92, 93. Computer science 59, 60. Computer science 63. Computer science 68. Electronics 41. Mechanical engineering 49. Mechanical engineering 56. Mechanical engineering 60, 60. Metallurgy 30, 30.
Ma'am, present. Hello, ma'am. Mechanical 60.
Mechanical 56. Okay. Now I have given. Okay. Metallurgy 30, 30. Actually, mining 26.
Yes, ma'am.
Has joined. Yes. Okay. Mining
26,
26.
ma'am.
Okay, okay. And last, mining 30, 30. 30.
Present, ma'am.
Mining 30,
Yes, ma'am.
30. Okay, okay, okay.
Yes, ma'am. Present.
So I think all of you have responded now, who were actually late in joining this classroom. Okay, thank you.